Okay, class, I wanted to go over the practical aspects of dealing with protecting data. And in the notes that I had provided in Module 2 of Week 6, I go over two schemes. One is very simple, and the other a little bit more complex, but it does a better job at protecting the data. So typically what we're going to experience for the rest of time with dealing with digital data is the fact that you're going to have a collection of or a series of ones and zeros or bits that'll be coming through a channel of some sort, whether it be a cable, a fiber line, a wireless channel, Bluetooth, anything, any medium that's going to be used to pass data through it. There is a vulnerability of sending data from one location to another. From a security perspective, it's important to be able to protect data so that when it gets to the other side or its destination, that the receiver has certainty that the data was received error-free. If somebody tampers with the data, the receiver should know that the data had been tampered with so that there's no potential of a violation of data integrity at the very least. Certainly if you're doing a transmission of data to a bank, you'd want to make sure that the data is being transmitted error-free, because if it happens to be corrupt along the way, what you expect to have happened may not be what's happening. So there is a whole host of data protection or data encryption algorithms that are used to protect data, to make sure that either A, it's just protected, or in the second methodology or the second protocol that we're going to look at, called the single error correcting code, there is a way not only of detecting if there's an error, but also correcting it so that the user doesn't have to resend the data again. Okay, so this particular video I wanted to put together so I could show you how to actually protect the data in a practical sense. The information provided in this video is going to make a lot more sense if you've actually gone through the theory in Module B. So I'm going to work through Module B with the understanding that you've already gone through the material in Module B and go through it from here. Okay, so in the first piece, it's called parity check coding. What a parity bit is an extra bit, or what they refer to as a non-information bit, that is added or appended to the data block. Now, data is available in different units, just like, you have, 2 eggs, or if you have 12 eggs, it's 1 dozen, 144 eggs is 1 gross. Data experiences similar terminology. The basic unit of data is a bit. A collection of related bits has a unit name. So 4 bits is a nibble, 8 bits is a byte, 16 or 32 or 64 bits is a word. In this case, just to try to keep it simple, I have 2 data blocks. It's just a nibble's worth of data, which is 4 bits. And we're going to try to protect the data with what's referred to as a parity check process. And what we're going to do is we're going to evaluate the data to be sent or to be transmitted, and we're going to evaluate it to find out what do we need to add to the nibble to protect it. It's a very, very simple protection mechanism. This particular methodology is only used to protect for a single error or a single issue with the data. If you have more than one error, this process is not going to work. Okay, so this is really simple, and as a result, all you need is a single parity bit. So the way that this works, and the information in Module B talks about what's referred to as exclusive OR math, or modulo 2 math, or modulo 2 sum. And what we need to, in order for me to go through this process, you need to understand what the modulo 2 sum is. And the way that it works is if you add 2 bits together, the only way that you actually get a logic 1 is if the 2 bits that you're adding together are different. So if you had 2 zeros, the modulo 2 sum is 0. If you have 2 bits, one is 0, one is 1, you would have a modulo 2 sum of 1. It's almost like adding the numbers together. So I'm going to put I'm going to add a couple of things here. I'm going to start doing some writing. So in the exclusive OR math, we have two possible values, and this is what the result of the value is. So there's only two possible choices for binary of values. That's 0 and 1. So we have a 0, 1, 1, 0, and 1, 1. This represents all possible variations of two particular bits. If we're dealing with binary and have 2 bits, the way that we work it is you take the base, which is binary or base 2, and you raise it to the power of the number of bits you had. In this case, I have 2 bits, so there's 4 possibilities. So you'll see that this is 1, 2, 3, 4. So if we were to add these two together, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. But because this is an exclusive OR, 1 plus 1 is equal to 0. It's a little bit different from adding the values together directly. So this is the basic idea of how we create our values. So the easy part about the parity check process is the fact that if we have to add one single bit. And in our case, we're going to pick what type of parity that we want. And so for the exercise we're going to do right here, we're going to be doing what they refer to as an odd parity protection scheme. And what that means is that the total number of bits that you're going to have when dealing with this particular protection scheme is you're going to have an odd number of ones. So since our data that exists, we have our data block of 1, 0, 1, 0. We now have to add our parity, and that parity is going to be, we have to have an extra bit, and we count the number of ones in our data block, which is, there's 2 ones, and to make this odd parity, we have to add an extra 1 for a total of 3 ones in the entire block. So the data that would be transmitted would be 1, 0, 1, 0, 1. Now, one of the things that I shared in the notes for this particular unit is that there's something called code efficiency. And the code efficiency demonstrates or is an indication as to how effective the scheme is that you're using to transmit information bits versus total number of bits. Okay, so the code efficiency of this particular code is equal to the number of data bits divided by the total bits. So in this particular case, for simple parity protection or parity check coding, we have the total number of data bits is 4. The total number of bits including parity is 5. And this means that we have an 80% efficient code, which is actually very, very high. But the reason why it's so high is because all we're doing is adding a single bit, in this case, a parity bit. Now, the scheme is pretty simplistic. It could only detect if there is an error. If it detects it, it can't correct it. And that's the point of the second scheme, which is single error correcting code. But let's go through and do the exercise on the next data nibble. And in this example, we're going to be doing an even protection scheme. So let's do an even parity protection. And in even parity protection, our data is 0, 1, 0, 0. We have to now add our parity. And since we have one single 1 and we have even parity, we have to have a 1 so that the total number of ones is even. So when we add this together, you'll notice that we have 2 ones. So the total data block that's going to be sent is 0, 1, 0, 0, 1. And that's what's going to be transmitted. Since we know that when we get to the other side, the receiver takes the responsibility of looking at this block of information and counting or adding the number of ones together. And if in fact you add the number of ones together, and it's supposed to be an even number of ones, you can detect if there is an actual error. But it's a detection, but it can't correct. And that's the responsibility when we deal with the single error correction code. Now, the single error correction code from the notes actually requires more work. It's not a lot of work, but there is a process that we have to go through in order to prepare the data for transmission. And then when we get to the other side, we have to go through a process of evaluating something called the syndrome so that we can determine if there is an error and where the error is. Okay, so again, I'm assuming that you've gone through the notes for the information in Module B. So if you haven't, my suggestion would be to put this video on pause, go through that information, and focus your attention on the single error correcting code, or the SEC code, in order to determine what the process is in order to go through this. So the first thing that we need to do is we've already got our parity scheme that we're going to be using, and that's going to be our even parity methodology. And we have our data bits, but we have to calculate our parity bits. Recall in the previous example, we calculated a parity bit based on the number of ones that was located in the original data block. In this particular case, it's a little bit more complicated. We have 3 parity equations that we have to solve. Now, this particular example is going to work for a nibble's worth of data. There is going to be additional parity bits required if you want to try to protect a larger data block. But at least this is just a process to show you the steps involved in protecting data, not just for a detection of an error or tampering, but also the correction of a single error in the scheme. Okay, so the important piece to remember as we have to prepare the data for transmission, we have to prepare the data for sending out, so that when it gets to the other side or the receiver has the equations that are necessary in order to determine if an error was made. Okay, so according to the protocol for the single error correction code, we have to create the model by which we're going to send the data out. So we have to come up with a protocol that we're going to be using as letters. So for this particular example, I'm going to use X's to denote data, and I'm going to use P's to denote parity. Now, the single error correction code is going to use 3 parity bits for every 4 data bits, which means that if you did the calculations, and it's actually listed in the single error correcting code portion of Module B, you find that the efficiency of this particular code is 57.14%. Now, obviously it's lower than 80%. And all that means is that the channel, Bluetooth, wireless, internet, wire, fiber, it doesn't matter. It means that when data is transmitted on that channel, it means that 57.14% of the time, data is being transmitted. Now, data is what we're looking for. It's the most important piece. But because we're trying to protect the data, we have to add some non-information bits, and those are the parity bits. So it drops the overall efficiency of the channel. It's just an is. Is it as efficient? No. But it does mean that you also have the ability to protect your information. So what we're going to do now is we're going to start creating the model, which is the placement of the parity bits and the placement of the data bits. So since the X's are the data and the P's are the parity, the model that we're needing to create is the model that shows the parity bits and the data bits as follows. It has to look like the parity scheme and the data scheme as follows: P1, P2, X3, P4, X5, X6, and X7. Now, It may look a little strange, but for this particular this protection scheme, this is how we have to interweave the parity bits with the data bits. Okay, so we already have our data bits, and what we do is we take the data bits and we place them into their respective locations within the protocol. Okay, so what we're going to do is we're going to have a 1, a 0, a 1, a 0. Now we have to calculate the P1, the P2, and the P4. But we'll get there. But we need to know this first, because when the equations for the parity bits reference x1, x3, x5, x6, and x7, we're going to get that information from here. Okay? I'm going to change colors so it looks a little bit different, so it's a little bit more of a contrast. But you'll notice that what's going to happen is we're going to have our equations in the notes for the single error correction code. It specifically has that P1 is equal to x3 exclusive OR with x5 exclusive OR with x7. Now, just to let you know, the reason why the symbol for the exclusive or the modulo 2 sum looks different from what's in the notes is because the symbol, when I was putting together the notes online, that symbol was not available to me. So the symbol that I'm showing you here, with the plus sign with the circle around it, is the true symbol for exclusive OR. I tell you in the notes that the symbol that I used in the notes is what we're going to be using for exclusive OR because I didn't have access to the symbol. But so let's take a look and let's do the transposition. X3, X5, X7. 1, 0, 0. So this is 1, 0, 0. 1, 3, 5, 7. 1, 0, 0. And if we exclusive OR these together, 1 and 0 is 1. And then we exclusive OR the 1 with the 0 here, which is 1. So this parity bit is equal to 1. For the second parity bit, the second parity bit is calculated by taking the exclusive OR of x3, 6, and 7. So P2, x3, x6, x7. And let's see what those values are. 3 is 1. 6 is 1. And then, sorry about that. And then we have 0. So 1 and 1 exclusive ORed is 0. And then when you add that with this 0, that's equal to 0. So that second parity bit is a 0. Now I'll go through the P4, which is equal to x5, x6, and x7. So 5, 6, 7. So it's 0, 1, 0. So I have 0, 1, 0, which is a 1. So those are my parity bits. And all I have left to do now is to put the embed the parity bits into with the data bits, and I have my transmitted data block. So my full data block, which is P1, P2, X3, P4, X5, X6, X7. Let's put it together. P1 is equal to 1. I'm done with that. And my P2 is equal to 0. I've got that. And then I have my, let me do my P4. I'm going to change colors of the pen. And then I have my P4 is a 1. And then I'm going to go back to red so you can see the data bits embedded. So it's 1, 0, 1, 0. Okay, so the full data block to be sent is 1011010. Okay, that's what is going to be sent using the single error correction even parity protection scheme in order to protect that data during transmission. Okay, so now what I'm going to do is I'm going to prove to you that we're going to try to see what's going to happen if we were to try to transmit this data, and we're going to identify a single bit being a problem. Okay, so we take this data and we transmit it over the internet, and somehow it gets intercepted and somebody messes with it, and somehow one of the bits changes because something went wrong. So I'm going to do something. We can pick one, and I'm going to pretend we know this beforehand. But now in the real world, you wouldn't know what was changed because when it was transmitted, it was error free. So I'm just going to circle this particular bit. This is the fourth bit, and one of the things that we're going to do is, if it's changed, if it's a binary number system, if it is changed, it's going to change to a 0. So this was sent originally. This was the data block that was sent. This is the data block that was received. And that is 1010010. So that's what was received on the receiving end. We don't know if it's error free. We don't know if it's good or bad. So what the notes tell you in Module B is that on the receiving end, we have to calculate something called a syndrome. And the syndrome is a collection of 3 calculations. And in the notes, I signify the representation of the syndrome is the letter B. And those are B's. And we have 3 calculations that we have to work on. But now to differentiate the P's, the X's, this is what was sent. If we want to differentiate what was sent with what was received, we're going to use the letter Y. So Y1, Y2, Y3, Y4, Y5, Y6, and Y7. And I'm just using the Y's to differentiate between what was being sent, which uses P's and X's, and what was being received. And I'm going to use the Y's in the equations for the syndrome to indicate that's what was received. If I were to use P's and X's, you would think that I was calculating the syndrome based on what was being transmitted or sent, not what was being received. So according to the notes, there are 3 syndrome equations, B1, B2, and B4. And here we go. The B1 portion of the syndrome is found by taking the odd components of the received bit stream. So Y1, 3, 5, and 7. And in syndrome, the B2 portion is 2, 3, 6, 7. And the B4 portion is found by taking 4, 5, 6, and 7. And all we have left to do now is to put the values in and calculate what the values are. Now, let me give you a little bit of insider information. If we come up with a syndrome of 0, there's no errors. If we don't, the syndrome is going to point us to where the error is. And when I learned this the first time, it really freaked me out that I was able to see a code that was being built, and all of a sudden I saw this code saying, hey, number 4 is bad. So what I'm going to do is, just to make it a little bit clearer, I'm going to go ahead and transpose the values from our the received block into our equations, here, here, and here. So 1, 3, 5, and 7. So 1, 3, 5, 7. 1, 1, 0, 0. So we have a 1, 1, 0, 0. It's supposed to be an exclusive OR symbol. So 1 and 1, exclusive OR is 0. 0 and 0, exclusive OR is 0. 0 and 0, exclusive OR is 0. So this right here is equal to 0. That's only one of 3 equations. The B2 portion of the syndrome is 2, 3, 6, 7. 2, 3, 6, 7. So 0, 1, 0, 1. So 0 exclusive OR with 1 is 1. 1 exclusive OR with 0 is 1. 1 exclusive OR with 1 is 0. That's the total. And if you want to do it a little bit easier, there's all zeros here except for these 2. 1 exclusive OR with 1 is 0. So that's the second portion. So far, it doesn't look like we have any errors. Let's take care of the last equation and see what we got. 4, 5, 6, 7. 4, 5, 6, 7. 0, 0, 1, 0. So 0 exclusive OR with 0 is 0. 0 exclusive OR with 1 is 1. 1 exclusive OR with 0 is 1. We got an issue. I don't know what the issue is, but we're going to find out. So what our syndrome is equal to, we put those bits together so that we can form what we need. And we have to put it in the right order. And that's B4, B2, B1. And according to what we have in our calculations, B4 is 1, B2 is 0, and B1 is 0. Now, I said before that if a syndrome is calculated to be 0, there's no errors. This is calculating a problem, saying the syndrome is 1, 0, 0. Now, if you were to convert this is a binary value. If you were to convert this binary value to decimal, or if you want to cheat and look at the summary of the notes at the bottom of the unit in Module B, you would find that 100 in binary converts to the bit, you want to guess? 4, which perfectly lines up with what we said before. If I go up a little bit, you notice that we messed up. We changed, this was transmitted with the 1, but somehow either somebody tampered with or something happened during the transmission process that the 1 turned to a 0, which means it's in the 4th position. The syndrome was calculated such that we were able to see that there is a problem in the 4th position. So what was received, let me change the color again. What was received was 1, 0, 1, 0, 0, 1, 0. That's what was received. The corrected version of the data should be 1, 0, 1, 1, 0, 1, 0. And this data should be similar to what we have in our transmitted data when it was first being transmitted. So, yes, what we learned is that by adding 3 extra parity bits before we transmit our data, we now have the ability that the code can find, not only detect an error, but it has the ability to tell the receiver, not only did I detect an error, but I can tell you which bit is the error. And that's what the wonderful thing about the single error correcting code scheme is. You lose efficiency, but you gain the ability to determine not only that there's an error, but which bit it's located in.